For more than 2,000 years, a machine with bronze gears sat on the sea floor beside statues and broken jars. It came from a Greek world with no engines, no electricity, and no glass computers. Yet it could track the moon, predict eclipses, and map cycles in the sky with moving parts. The strange part is not that it existed. The strange part is how a device this smart vanished so completely. By the end, you'll see why this machine changes less about the future and more about what we thought the ancient past could never do. Picture a small island between Greece and Crete. The water around it is beautiful, but not friendly. Strong currents twist around steep underwater slopes, and sudden weather can turn the sea into a trap. That island is Antikythera, and just off its coast sat one of history's most important accidents. In the spring of 1900, sponge divers from the island of Symi took shelter near Antikythera after bad weather pushed them off course. When they dropped below the surface, they did not find an empty seabed. They found a shipwreck, and not just any wreck. Scattered across the bottom were statues, glassware, pottery, coins, and luxury goods. It looked like a floating museum had crashed into the deep. The ship had gone down in the first half of the 1st century before the Common Era, likely while carrying expensive Greek goods westward. Nobody knows exactly where it was headed. That question still hangs over the wreck. The recovery was dangerous from the start, and these were early deep dives in heavy suits, with limited understanding of how the human body handles pressure. Men went down on air hoses and lines, working in cold water around jagged debris. Even getting artifacts to the surface carried a cost. The sea gave up its treasures slowly and not kindly. At first, the most exciting finds were easy to understand. Marble statues looked like art, bronze figures looked like art, decorated vessels looked like art. Then there was one ugly lump of corroded metal and wood that looked like nothing at all. That lump was brought up in 1901. For a while, it drew less attention than the statues. You can understand why. If you were standing in a room full of ancient sculpture, would your eyes go to the broken green crust in the corner? Then the crust cracked. Inside were teeth, not animal teeth, gear teeth, tiny ones, carefully cut, set in circles, meant to turn against each other with control and purpose. In that moment, the object stopped being debris and became a problem. Ancient writers described clever machines. Greek engineers built pumps, water clocks, stage devices, and mechanical tricks. Philosophers and astronomers studied the heavens in serious detail, but nothing that had actually survived from the ancient world looked like this. Nothing so compact, nothing so geared, nothing so ambitious. Today we call it the Antikythera mechanism. It was built from bronze and once sat inside a wooden case about the size of a shoebox. A handle turned its internal gears. Pointers moved across scales. It did not store digital code, of course, but it did something just as shocking for its time. It turned astronomical ideas into motion. That is why people often call it the world's first analog computer. Analog here means it modeled real cycles through physical movement. Instead of numbers flashing on a screen, bronze wheels turned and made the sky legible. You did not read it like a text, you watched it think. But here is the detail that keeps pulling people back. This was not just a calendar with fancy parts. It was a machine that encoded relationships in the heavens. If one gear turned by a certain amount, another pointer moved to show where the moon should be, or when an eclipse cycle returned. A theory became a mechanism, and that makes the silence around it even stranger. Europe would not leave behind similarly complex, geared astronomical clockwork until more than 1,000 years later. That does not mean the ancient Greeks were building smartphones. It means one branch of technical skill grew bright, then almost vanished from the record. The gap is what feels impossible. Before we get to how it worked, we need to sit with that gap. History often looks solid because books and museums make it seem solid. But the past is not a complete shelf. It is a pile of survival. Stone stays, pottery stays, bronze can be melted down, wood rots. Fine instruments disappear first. So when people say the mechanism should not have existed, that is not quite right. A better way to say it is this. It should not have been our only surviving witness. If a device this advanced existed, it likely had ancestors, makers, and maybe rivals. We just do not have them. That idea changes the whole mood of the story. This is not one miracle dropped from nowhere. It is one survivor from a lost tradition. And once you see it that way, every broken fragment starts to feel less like a puzzle piece and more like evidence from a vanished workshop. The wreck itself helped set the stage. The ship was carrying high-value cargo in the Roman era, probably as Greek art and luxury goods moved toward wealthy buyers. The mechanism may have been cargo too, or a personal item, or a teaching device, or a prized possession packed for travel. The wreck froze one moment, then erased almost everything around it. Now imagine the object after 2,000 years underwater. Bronze fused with mineral deposits. Wood collapsed. Surfaces were scarred by corrosion. The mechanism eventually separated into dozens of pieces. Researchers now work with 82 known fragments, and only about a third of the original device survives. That missing 2/3 is where the tension lives. For years, scholars could only study the outside. You can only guess so much from a corroded shell. Clean too hard, and you destroy evidence. Leave it untouched, and the answers stay trapped inside. It was like owning a burned book where the pages were fused shut. Still, early researchers saw enough to know this was no ordinary object. Radiographic work revealed gears. More than that, it revealed complexity. About 30 surviving gear wheels have been identified. Some reconstructions need more lost gears to make full sense of the system. That matters because the mechanism is not solved like a crossword. It is rebuilt by evidence and restraint. One of the first people to change the conversation was historian Derek de Solla Price in the 20th century. He argued that the object was an ancient Greek astronomical calculator. His model was not the final answer, but his main insight was huge. The gears were not decorative, they computed. That single shift opened the door to a century of careful reconstruction. Later, museum curator and engineer Michael Wright pushed the story further. He explored whether the front of the machine may have shown planetary motion, not just the sun and moon. In other words, the device may have been even bolder than earlier models allowed. But the real leap came in the 21st century, when researchers got a way to look through the corrosion without tearing the fragments apart. In 2005, high-resolution X-ray imaging and surface scanning exposed hidden details inside the metal. Suddenly, gears, shafts, and inscriptions buried for nearly 2,000 years came back into view. And the inscriptions were a gift. Thousands of faint Greek letters appeared. Some were labels, some looked like instructions. Some described cycles, displays, and celestial behavior. The machine had not just survived as hardware. It had left behind part of its own damaged manual. That was the moment the story changed from wonder to evidence. Now researchers could test models against what the object itself said. If a theory did not fit the surviving gear teeth, or the available space, or the inscribed labels, it had to go. You could still imagine boldly, but you had to imagine honestly. So what is firmly known? The back of the mechanism is the clearest place to start. It carried large spiral dials that tracked long astronomical cycles. One major dial represented the Metonic cycle. That is a pattern linking 19 solar years to 235 lunar months. In simple terms, it helps line up moon months with the solar year. That may sound abstract, but it mattered deeply in the ancient world. Calendars did not just tell people what day it was. They organized festivals, rituals, civic life, and agricultural timing. A machine that helped reconcile the sun and moon was not a toy. It was a way to keep human time in step with cosmic time. The upper spiral dial on the back is understood as this Metonic cycle. A pointer moved through the spiral as the years advanced. Smaller connected displays likely handled longer corrections, such as a 76-year cycle called the Callipic cycle. The names can sound heavy, but the core idea is simple. The machine tracked repeating patterns with nested precision. The lower spiral on the back was even more dramatic. This dial represented the Saros cycle, a pattern of 223 lunar months, or about 18 years and 11 days. Over that span, the geometry of the sun, earth, and moon repeats closely enough that eclipses return in related patterns. The mechanism used that repetition to predict eclipse opportunities. Not predict in the modern sense. It was not solving gravity equations the way modern astronomy does. It was using accumulated cycles. But that does not make it crude. It means ancient observers had learned enough from the sky to turn recurrence into reliable expectation. Think about how powerful that would feel in the ancient world. An eclipse was not just a science fact. It could seem like an omen. It could affect politics, war, religion, and fear. If you could turn a handle and show when eclipse months returned, you were not just demonstrating skill. You were demonstrating command of patterns most people never saw. Some of the markings in the eclipse dial seem to indicate more than just whether an eclipse was due. They suggest details about type or appearance. There was also a smaller dial linked to a longer eclipse correction cycle. In short, the back of the mechanism was not casual. It was a serious astronomical tool. Then there's the part almost nobody expects. One smaller dial tracked the cycle of major athletic festivals, including the Olympics. That one detail changes the flavor of the whole device. It tells you the mechanism was not separated from culture. The sky, the calendar, and public life were woven together. That is easy to forget from our modern view. We treat astronomy, sports, religion, and calendars as separate drawers. Ancient users did not always see them that way. A machine that organized celestial cycles and festival timing was serving a lived world, not just a classroom. Now we move to the front. This is where certainty thins out and the story gets even better. The front of the mechanism is harder to reconstruct because much less survives. Scholars agree that it had circular scales, including a zodiac ring and a calendar ring. A pointer for the sun seems secure. A display for the moon is also secure, along with a way to show lunar phase. But the front is where the greatest missing pieces live. And this is where the machine starts looking less like a fancy clock and more like genius compressed into bronze. The moon does not move across the sky at a perfectly steady speed. Its orbit is not a perfect circle, so its motion appears to speed up and slow down. The mechanism modeled that irregularity mechanically. It used a pin and slot system with offset gears to imitate what Greek astronomy believed the moon was doing. Read that again in plain terms. Ancient makers built a machine that could make motion look uneven on purpose, because the real moon looks uneven from Earth. This was not counting days. This was simulating nature. That feature alone is enough to stop you cold. It means the builders did not only know cycles, they knew how to express a subtle astronomical theory in rotating metal. They had turned geometry into touch, and yet the front may have done even more. Inscriptions refer to the sun, the moon, and the 5 planets known in antiquity: Mercury, Venus, Mars, Jupiter, Saturn. Those are the wandering stars visible to the naked eye. In Greek cosmology, they moved in ways that could appear to slow, stop, reverse, then move forward again. Representing that on a compact machine is hard. Doing it with missing parts is even harder. That is why the front has fueled decades of debate. Researchers are not only asking what the machine did, they are asking what ancient builders thought was worth showing, and how they fit it all inside such a small case. This brings us to one of the biggest recent turning points in the story. In 2021, a University College London team published a major proposed model for the front display. Their goal was not to tell a flashy tale. It was to see whether the surviving fragments, inscriptions, and ancient astronomical cycles could support a coherent planetary system at the front. Their answer was yes, or at least very likely yes. The team proposed that the front displayed the sun, the moon, and all 5 known planets moving through the zodiac. Their model used compact nested tubes and gear trains packed into the available space. It also tried to match numerical clues in the inscriptions, including long cycles linked to planetary motion, such as those for Venus and Saturn. That matters because the model did not come from fantasy. It came from constraints. The gears had to fit, the outputs had to match the text, the mathematics had to make sense in ancient terms, and the whole thing had to remain buildable with known techniques. That is what makes a serious reconstruction different from a cool animation. Still, the UCL team did not claim total victory. They were careful. Their model, in their own framing, was the first that aimed to conform to all the physical evidence and the scientific inscriptions. But not all the original parts survive. So no one can say with absolute certainty that every proposed front gear is exactly what the ancient builder used. That caution is not weakness. It is the reason the research matters. Real science gets stronger by telling you where the edges are. And yet, even with that caution, the idea is breathtaking. Picture a handheld machine from ancient Greece showing the sun, moon, and planets moving through a structured cosmos. A small box, a few bronze plates, a handle, and inside, a working argument about the universe. That is the emotional peak of the whole story. Not because it sounds impossible, because it sounds human. Somebody had to imagine the display. Somebody had to choose the cycles. Somebody had to calculate ratios. Somebody had to cut the teeth. Somebody had to label the case. Somebody had to believe this much knowledge could live in an object you could hold. That is the revelation that really changes history. The mechanism does not tell us ancient people were secretly modern. It tells us that intelligence does not move in a straight line. A society can become brilliant in one narrow craft, then lose it. The past had peaks we do not always see because survival is uneven. And if you think that is the end of the mystery, it is not. Because even after the scans, even after the UCL model, even after decades of work, the mechanism keeps giving researchers one more question. One of the recent debates concerns the front calendar ring. For a long time, many assumed it carried 365 holes, matching a solar year. That sounds reasonable. But the ring survives only in damaged pieces, not as a perfect circle, so the total had to be inferred from fragment positions. The newer analysis pushed back. Researchers studying the surviving hole positions suggested the count might be closer to 354, which matches a lunar year of 12 lunar months. That alone would shift how we understand the front display. In 2024, astronomers at the University of Glasgow applied statistical methods to the problem. These are techniques also used in modern research on gravitational waves, the faint ripples in space-time measured from cosmic events. The idea sounds almost poetic. Tools built to study the universe today were used to examine the spacing of tiny ancient holes. The result favored about 354 or 355 holes, not 365. In other words, the ring was much more likely lunar than solar under their assumptions. That does not settle everything forever. Damage, deformation, and measurement choices still matter. But it strengthens a very important interpretation. Just pause and enjoy the scale of that sentence. A bronze device from ancient Greece is still producing new science in the 21st century. Not because it is magical, because it preserves just enough information to test. The machine remains active as a question. And maybe that is why this story never grows old. Every answer solves one layer and reveals another below it. Decode the back dials, and the front becomes more mysterious. Model the front, and the calendar ring changes shape. Measure the ring, and you start asking what workshop could drill holes that precisely by hand. That last part deserves attention. The 2024 analysis also pointed to remarkable precision in the hole spacing. Not machine shop precision by modern industrial standards, of course, but astonishing care for a hand-made object more than 2,000 years old. You can almost feel the steadiness required. This brings us to the deeper explanation. How could a machine like this exist in the ancient world at all? The answer starts with the sky. Babylonian astronomers had recorded long cycles and repeating patterns for centuries. Greek astronomers and mathematicians developed geometric ways to model celestial motion. Philosophers argued about cosmic order. Engineers understood toothed wheels, bronze work, and controlled motion. The pieces already existed. The mechanism matters because someone combined them. That is a different claim from saying the Greeks randomly leaped ahead of history. They did not build this device in an empty field. They inherited observations, refined theories, and practical craft. The machine is the point where those streams meet. Ancient literature even hints that similar devices once existed. Cicero described celestial mechanisms associated with Archimedes and with the philosopher Posidonius. We do not have those instruments, but the references matter, because they show the idea of mechanical cosmos displays was not unthinkable in the classical world. That does not mean Archimedes built the Antikythera mechanism. He almost certainly did not. He died too early. But traditions linked to men like him may have shaped the intellectual world that made such a device possible. Influence is not the same as authorship, and that distinction matters. Hipparchus also enters the conversation. He developed lunar theories closely related to the kind of irregular moon motion the mechanism seems to model. Again, we must be careful. We cannot simply name him as the designer, but his work shows the right kind of astronomy existed. So the real question is not whether ancient people were smart enough. Of course they were. The real question is how many people, in how many places, had to work together to produce one mechanism like this. Think of the hidden chain behind it. Someone needed bronze. Someone needed tools to cut teeth and drill holes. Someone needed tables of cycles. Someone needed to translate those cycles into gear ratios. Someone had to solve the physical layout so the system fit inside a shallow case. Someone had to engrave labels. Someone had to test the result. That is why many researchers think the mechanism implies predecessors. A device this polished probably did not appear as a first attempt. It feels like the visible tip of a tradition. The problem is that traditions in metal and wood can vanish almost completely. A book can survive by being copied. A machine survives only if someone preserves it, repairs it, or builds another one. If a workshop closes, if patrons disappear, if a city falls, if bronze gets melted down, the line breaks. Knowledge stored in hands is more fragile than knowledge stored in texts. And even texts can be misleading. A copied astronomy text can carry abstract theory forward for centuries. But if the craft link between scholar and artisan breaks, the mechanical version may die. You can preserve the idea of the sky while losing the ability to build a working model of it. That may be exactly what happened here. The Antikythera mechanism also helps break one of our most common mistakes about history. We imagine progress as a smooth staircase, up and up, century after century. But real history does not behave that way. It looks more like islands, bright clusters, local peaks, lost roots. A civilization can master one domain, then fail to carry it forward. Another civilization can rediscover similar principles through a different path. That is why it is wrong to say this machine proves the Greeks had secret industrial technology. It proves something more interesting. Human ingenuity can flare in very specific forms. And the mechanism itself was not flawless magic. It had limits. Its triangular gear teeth were hand-cut. Its plates were thin. Any real device would have had friction, tiny errors, and wear. Its eclipse predictions were based on cycles, not modern orbital physics. It was brilliant, but it was still ancient craftsmanship working within ancient models. That actually makes it more impressive. Because now you are not picturing a fantasy machine with impossible tolerances. You are picturing real craftspeople, using files, drills, bronze sheet, and accumulated skill to create a device that performed useful astronomical calculations with moving parts. It was not perfect. It was good enough. And good enough, in this case, was astonishing. Modern reconstructions can sometimes hide that truth. A polished museum replica can look cleaner and more certain than the artifact ever was. It can trick you into thinking all the questions are solved. But every reconstruction is also an argument. It proves what could work, not always what did work. That is why the fragments remain the final authority. Surviving gear teeth limit possible ratios. Holes limit shaft positions. Inscriptions limit possible displays. Empty spaces limit what missing parts could have been. Good researchers are not trying to force a story. They are trying to obey the object. And the object keeps resisting easy endings. Who commissioned it remains unknown. Who designed it remains unknown. Who built it remains unknown. Even the exact date of manufacture is debated, though around 100 before the Common Era is a common estimate. The ship sank later, so the mechanism may already have had a story before it ever boarded that vessel. Was it newly made when it traveled? Was it repaired and reused? Was it a rich man's educational instrument? Was it a gift? A sale item? A scholar's tool? A display piece meant to impress guests? The gears cannot tell us why it was on that ship. That absence makes the mechanism feel strangely personal. Someone turned its handle. Someone watched its pointers move. Someone read its inscriptions. Someone expected to arrive somewhere with it. Then a storm or error or bad luck ended the journey. The calculation stopped in transit. And maybe that is why the machine captures people who normally do not care about technical history. It is not just a device, it is an interrupted life. Now imagine it when it still worked. You stand in a dim room, maybe lit by oil flame. The wooden case opens, scales and labels appear, a hand turns the handle. The sun advances. The moon changes phase, a pointer creeps toward an eclipse marker. Somewhere on the display, a planetary motion reverses against expectation. You're not looking at nature directly. You are looking at a model of nature performing itself. That experience must have been powerful. It made invisible cycles visible. It took years, decades, and generations of sky watching and compressed them into a physical show. In a sense, it let a person handle time. This may explain why the mechanism joined both science and spectacle so naturally. Today, we often split those things apart. Either tool is rigorous or it is dramatic. But the mechanism may have been persuasive because it was both. Accuracy gave it authority, motion gave it awe. That combination still works on us now. Planetariums do it, simulations do it, animated maps do it. We trust ideas more easily when we can watch them move. The Antikythera mechanism may be ancient proof that visualized knowledge has always carried special power. There's another lesson hidden here too. When we think about the ancient world, we often picture monuments, temples, statues, roads. Those are stone stories. They survive because stone survives. But a culture is not only what it builds in stone, it is also what it calculates, teaches, fixes, and carries. Precision instruments are bad at surviving. Bronze can be reused, wooden cases collapse, fine shafts bend. Small machines get stripped for parts. The archaeological record is not lying to us, but it is filtering the truth. It favors what could not be recycled and what happened to be buried or sunk. The Antikythera mechanism passed through that filter by pure luck. A ship sank in the right place. Divers found it. The right fragment came up. Someone noticed a gear. Conservators kept it. Imaging technology arrived before the evidence was lost beyond reading. A chain of accidents preserved a chain of gears. That is why the mechanism does not just change what we know. It changes how humble we should be about what we do not know. If one smartphone survived from our age and everything else vanished, future people might think it was an impossible object. But it would only be one surviving endpoint of a huge hidden system. Mines, factories, coders, shipping routes, standards, schools, power grids. The phone alone would hint at all of them. The Antikythera mechanism works the same way on a smaller scale. It implies astronomical tables, design knowledge, bronze suppliers, skilled engravers, gear cutters, wealthy patrons, and probably earlier devices. Most of that world is gone. The mechanism is what leaked through. This is the true shock. Not that the Greeks built something too advanced to be real, but that our surviving record of what they built is so incomplete that the real thing can still feel unreal. Researchers are still going back to the wreck. Modern archaeological work at Antikythera uses far better diving systems, mapping tools and excavation methods than the sponge divers had. New objects continue to come up. Human remains, ship parts, cargo fragments, clues about how the vessel was built and what it carried. And every new dive raises the same tantalizing hope. What if more mechanism fragments are still down there? Imagine finding one more plate with a few engraved words, or missing gear with a clear tooth count, or part of the front display. A single small piece could settle major arguments that have lasted for decades. The sea does not organize evidence by importance. The most crucial part may still be under rock or sediment. There's also the bigger hope. What if another device like this is found somewhere else? That discovery would transform the story again. The Antikythera mechanism would stop looking like one lonely miracle and start looking like the first survivor in a family we forgot. It would not become less important. It would become more understandable. Until then, it stands alone, and standing alone invites wild stories. That is why this object gets dragged into ideas about aliens, lost supercivilizations, or impossible technology. But none of that helps. The truth is already stranger than the fantasy. Humans built it. That is the point.